Good morning. Well, hopefully by now you've uploaded your demand estimation summary and the supporting details and the written discussion of what assumptions you made and what data sources you've utilized. I think it's really important for me to give you feedback as quickly as possible, and so I'm going to make that a priority to look over it as quick as I can. And I'll upload the feedback on MU Online, and you can begin the next phase of the project before you hear from me, because what you're going to be doing is laying out the pipes. And there's two aspects to that. There's laying out the location of the pipes so that you minimize the overall length of pipes that's being used. And then there's optimizing the size of the pipes. Now, of course, optimizing the diameter of the pipes is going to depend on what flow rates you assume is coming out of the network. We'll talk about that a little bit in a minute. But the point is you can make sure the program is installed on your computer. You can learn how to import the JPEG file in the background. And the advantage of doing that is that then you can draw your network right on top of a map in the background. Now, unfortunately, for whatever reason, it's been my past experience that the image doesn't come in particularly clear. I mean, it's not really as sharp as you maybe would expect it to be. It's sharp enough that you know where things are, but it's not going to look like $1,000,000 is the point. Okay, so you've got a little bit of time to start thinking about that. More immediately, what's on your radar is homework number 8 and quiz 2, both of which are going to be on our next class meeting on Tuesday. And of course, this quiz has a pretty narrow focus on the coverage. It's just going to be the last 2 classes, and today's class is going to be the topic of that quiz. So we're going to continue talking about Manning's equation today and some issues related to channel geometry and how we can maximize flow rate through channels. Are there any questions related to the announcements? Jeremy? Okay. So what's your question?
I didn't know if anybody else had the same problem. Because I tried to right-click on it and save as, and I also tried to open both of them for not showing off.
Okay. Well, maybe that's something we can take a look at after class. Are there other questions related to the announcements? All right. So the next phase of your project is sizing the pipes. And this is kind of a strange view. This is looking at a pipe network from beneath. And of course, this is an imaginary view. This is not something that can occur since the pipes are buried in soil generally. But the reason why it's so important for those pipes to be big enough is that if they're not large enough, you can't deliver an adequate flow rate to the locations that need to receive it. Remember, you can't suck water out of a pipe. Not very effectively because of the risk of cavitation. So water has to be pushed through a pipe. So if there's a certain demand, whether it's at a hydrant or at the pipe that comes into a building, it's the pressure that's at that location that determines how much water can make it through the pipe at that location. And so the combination of pressure and pipe size is what you're going to be optimizing in the second phase of the project. Now, if the pipes aren't big enough and you can't deliver enough water, then it has economic, it has health implications. People get very angry, and so there can be social effects as well. Buildings can catch on fire if there isn't adequate water to put out the fires. So it's really important that the pipe network not fail, but then at the same time you're trying to balance the need to optimize. In your project, I've instructed you that the design flows are going to be the larger of the maximum daily demand plus fire, and of course it's only the residential areas we're assuming have fire demands. And the rationale for that is that we're assuming commercial areas and industrial areas have fire suppression systems that would reduce the risk of fire, so that it's only the residential structures that have a demand on the pipe network itself. So the larger of that or the maximum hourly demand. Now, not all of the flows, as you know, are going to be peaked. The flows that are peaked are generally those that have some sort of a human component. So in the case of a sports stadium, when is the water demand going to be the most in a sports stadium? It's probably, if it's a football game, for instance, at halftime, when everybody is taking a break, going to the restrooms, simultaneously using a lot of water. Or in the case of residential demands, it's in the evenings when everybody turns on the washer, starts a load of clothes, is taking a shower, all that water demand all at once. But in contrast to that, the water demands at the food processing plant are probably pretty constant because presumably there's some sort of an industrial process there that's just it's in continual operation. And I told you, I think, how many million gallons of water per week is used at that food plant. Now, it's probably not used 24 hours a day, 7 days a week. At least that's not the conservative assumption. The conservative assumption would be that the water is being used maybe 40 hours per week. So you have a fewer number of hours that volume of water is being consumed, and so that's going to increase the flow rate going out at that location. And the same kind of idea is going to apply at the golf course. Maybe what you did was you looked at during the drought periods, like the driest year, the driest month in the last X number of years in your town. How much rainfall are they getting versus how much water does the grass need at the golf course. And so maybe you found that the difference between those two is you need to provide half an inch of water, and you multiplied it over the area, and you've turned it into a volume of water that has to be delivered. But now consider, is that golf course going to be watered 24 hours a day, 7 days a week? If people are out there golfing, the water's not going to be on. They're not going to be watering the grass while people are trying to golf. And so generally what the courses will do is in the evening hours, when temperatures are lower and there's reduced wind to try and prevent evaporation, that's when a lion's share of the irrigation would occur. So you kind of need to think about when the water demand is going to occur, but then at the same time trying to construct this nightmare scenario that ensures that the pipe sizing is big enough. The nightmare scenario would be that there is a fire somewhere on this peak day at the peak hour when there's also a sports event going on and the hospital is already full, so it has maximum demands. All of these things are happening simultaneously and your pipe network isn't going to fail. The design criteria that you're going to apply is that the pipe network pressure should at no time go outside the range of 240 kilopascals at the low end to 850 kilopascals at the high end. You have to design this pipe network and analyze it at two different conditions. You want to see what's going to happen to this pipe network when there's zero flow. Because when there's low flow rates or no flow, like in the middle of the night, when the pipe network doesn't really have any demand coming out of it, it's just going to be the static pressure. And remember that what's pressurizing this network is that up on a hill is a tank. And that tank pressurizes the network. So at night, when there's no demand, then essentially the pressure at any location is going to be largely dependent on how high above that pipe elevation is the water elevation. And that's when you're going to see this high pressure, no higher than 850 kilopascals, hopefully. So the low flow condition, what you're going to be really determining is how high on the hill can you afford to put that reservoir. And putting it pretty high on the hill is a good thing because it's free energy. The more you pressurize your network, then the smaller the pipe diameters can be. Like if you said, well, I'll just make it so that at night when there's low demand, I'm just going to make my max pressure 500 kilopascals. Well, the problem with that is that during the day, when you do have a lot of demands, now you don't have as much pressure to work with. When there are losses during the day, you want to start with plenty of pressure so that the losses can bring the pressure down, but not any lower than 240. So I think that you'll get a feel for this iteratively as you go through the program and you choose a new location for the tank or the reservoir on the map, and you type in the elevation of the ground at that location, and then you see how does the pipe network behave when you move the reservoir around and therefore have a correspondingly different water elevation. Minimizing the pipe diameter is going to save your client money because, as the handout identifies, the larger pipe diameter has more material, and so it costs more both just on a material basis, but also the installation becomes more difficult because now the sections have to maybe be put into place with heavy equipment rather than put into place by hand, and so just everything becomes more complex and more challenging when the pipe diameter increases. Now, just for simplicity, what you can assume is that the elevation of the ground surface is the elevation of the pipe. And if you want to offset it below the ground surface, 5 feet, then that's fine too. You can do that. It's not going to change any of the calculations, but the point is that when you're laying out the location of the pipe, you're going to have to put into water gems the elevation of that junction so that it knows the difference between the upstream junction elevations and the location that you're working with. When you think in terms of the energy equation, that's what water gems is going to be solving, is it's going to be solving the energy equation. And so for it to tell you what is the pressure at any point in the network, it's going to be calculating the head losses, it's going to be calculating local losses, it's going to look at the elevation difference, it's going to know the flow velocity. So all those things are going to be taken into account when it calculates the pressure. Yeah?
For pipe sizing, should we consider like future growth and increase the flow?
Great question. The future growth assumption is already built into your demand estimation. And so like those population densities that I told you to assume, those we're assuming are the population densities when this area is totally built out. And so right now it's raw demand, and for the first number of years when this development's in place, probably the pipe infrastructure is going to be way bigger than it needs to be. Think about Tanyard Station. Has anybody driven past that on Route 60 where the Aldi is right now? And presumably there are some pipes going into that development, and right now they're not getting much use because all that's over there is like a steakhouse, the Sheetz, and Aldi, a few other things. But the point is that they designed the roads, the off-ramp from Route 60, the pipes. They designed all of that thinking that eventually it's going to be built out. So you don't need to put any kind of additional capacity into your network beyond the demands that you've already estimated. Are there other questions about the project? So your action item, even though your main focus is this homework assignment and the quiz, I would strongly encourage you to install the software today if you don't already have it installed. And I'll check to see if there's any underlying issue with the JPEG or what's going on with that. And if I need to upload a different file to MU Online, then I will. But it's worked in the past, so hopefully things haven't changed. All right, well, let's just get our beaks wet with another Manning's equation example. Have you already memorized Manning's equation? You getting pretty close? You don't have to memorize it for the quiz, but I think naturally you're going to come to memorize Manning's equation pretty quickly. So if we combine the hydraulic radius, which, hydraulic radius is area divided by wetted perimeter. So if we combine the area that gives us flow rate rather than flow velocity with the area that's built into the r to the 2/3 power, this is the expression of Manning's equation that I think makes a lot of sense. Last time we focused on solving Manning's equation for flow depth. So that's probably the trickier of the two kinds of calculations that we'll take a look at. Today we're just going to solve for the flow rate. And by the way, I sent you the link for the video on how to use an HP. I don't see any shiny HPs. not yet anyway. Maybe it's just being shipped, and honestly, I don't care either way. As long as you can solve trapezoidal channel geometry, solve for the depth, and that's good. This one's easy, though. What we've got is a trapezoidal channel where the bottom width is 3.5, the known depth is 1.2. The side slopes are defined as 2.5 to 1. And so what we know is that if it's 1.2 meters deep, that tells us how much extra top width we've got, right? So if the depth, if y is 1.2 meters and the bottom width is 3.5, the fact that we have 1 to 2.5 side slopes means that for every vertical unit, then the side triangle on either side, the top width of that side triangle for each unit of vertical is 2.5. So if this is 1.2, then that means that the sides are going to be 3 meters, each side here. Okay, and so then it's 3.5 there, and another 3 meters on the other side of the triangle. So 1.2 times 3.5 gives us part of the area, and then these side triangles can be combined into a rectangle that has an area of 3 by 1.2. So use Manning's equation here with the given end value for a smooth asphalt, the given bed slope of 0.001, and find what's the flow rate. Remember, these are the this is the formulation for traditional units. If this was BG units, then there'd be the 1.49 in front. But since this is the SI units, it'll give us cubic meters per second on the left side of the equation when we use meters squared for area, slope is unitless, end value is unitless, wetted perimeter is going to be units of meters. All right, so let me pause for a moment and let's see if we can calculate the flow rate for this one. So on this one, probably the tricky thing is identifying the wetted perimeter length. I mean, if anything's tricky, it's just recognizing that this distance from the water line on the side down to the bottom edge, that distance is going to be the square root of 1.2 meters squared plus 3 meters squared. So we're trying to find the length of the hypotenuse of that triangle. And there's two of them because there's one on the left and one on the right. So here where I'm calculating the wetted perimeter, it's going to be the bottom width of 3.5 meters and then 2 times that side length. So the total wetted perimeter, 9.9622 meters. And then we just substitute everything into Manning's equation. Do you remember what the assumptions of Manning's equation are? Steady flow and uniform. Yeah, steady uniform flow. So this has to be applied in conditions where the flow rate isn't changing over time. Well, it doesn't have to be applied in those conditions. It could be applied in any conditions, but if you want it to be accurate, then it's only going to be applicable when conditions are not changing in the direction of flow. So it means that you have basically a channel that isn't changing shape, the slope isn't changing on this channel, the flow rate isn't varying over time. Essentially, it's in an equilibrium condition. And so it's approximately 15 cubic meters per second for these conditions. All right, so are there any questions on this example? All right. Here's a picture of a device that's used to measure what the velocity of the water flow is. And so you can see that what they do is they have a little impeller that goes down into the water, and as the water passes around it, it spins. And it's calibrated because the water, as it flows through it, is going to be moving faster than would be indicated directly by that spinning. You know, the spinning of it, there's going to be some drag, and so they probably have correction factors that are built into the instrument that's on the top of the tube, where they know that, you know, if you have 1 meter per second going through this opening, then probably the surrounding water is flowing at maybe 1.1 meter per second. So they figured that all out in the lab. And now what they can do is take this into the field and measure what is the flow rate by knowing what's the flow velocity at any point, and then integrating that over the width of the channel. And so to know what's the flow rate in a river, what you'd have to do is take this device and you'd have to measure at different locations in the river, all the way across from bank to bank, what's the flow velocity, and you'd divide your flow area into segments, and you'd say maybe at 1 meter intervals you'd find out what's the velocity, and then you could assign the velocity at that 1 meter segment, multiply the velocity by how wide it is and the depth of the water at that location. And so then that would be a way of numerically integrating the cross-sectional area of the channel to find out what's the flow rate. But of course, one thing that would be tricky about that is the way I just described it, you were finding a flow rate that you'd use for each maybe 1 meter width segment. But as you might expect, the flow velocity is changing as you go up and down in the channel. So there are a variety of equations that allow us to predict what the flow velocity is at a certain depth. Now you could actually measure it directly, but now think about how tedious that's going to be, especially for a river the size of the Ohio River here. If we were going to go in 1 meter segments and then measure at depths of, I mean, even if you did it at 1 meter depths, now you're talking about hundreds of velocity measurements, so that probably by the time you got to one side of the river, now conditions have changed and the amount of time that it took you to do that. And so rather than always relying on direct measurement, there are ways to say what's the velocity as a function of depth, predicting it just based on the average velocity. So the most complicated of the empirical formulas that your book introduces is this von Karman equation, where just through a lot of observation out in the world, they came up with a function that took the following factors into account: the slope of the channel, how deep the flow is at a certain location, and then based on the depth of flow and the slope of the channel, what this equation allows you to do is, for a certain distance away from the bottom of the channel, so that's what they're using here for y, so the ratio of y to d, when you're at the very top of the river, then y to d would be 1. And so just I graphed this von Karman expression for 2 different slopes to see, you know, is it sensitive in the way that we'd expect it to be for different slopes. And what the function graphs out to show is that when you have a steeper slope, so this light red line is the steeper slope, the velocity profile is more extreme, meaning that the water at the top is moving faster than as you get further down into the flow. Now, this function is a little bit weird because it'll actually produce negative velocities at the extreme. And of course, that doesn't make any sense that at the bottom the water would be going the opposite direction. And so this function is really only useful for predicting maybe the upper 4/5 of the water column, the velocity at the upper 4/5 of the water column. There are simpler approaches to this as well. I mean, one approach has just been that one of the ways to find the average velocity is to measure the velocity at about 4/10 of the depth. So if you go down a certain distance, they've observed that it's approximately equal to the average depth at the measured velocity 4/10 of the way to the bottom. Or maybe another way of taking differences in slope into account is by having a weighted average of the velocity 2/10 of the way from the top, 2/10 of the way from the bottom, averaging the two, and then that would give you the average velocity. So these two functions are used for approximating the average velocity based on one measured location rather than measuring at all of the depths. And then this equation would tell you if you have one measured average velocity, or another way to know the average velocity is if you have a known flow rate and you know the cross-sectional area. Remember that V is Q divided by area. So if you know Q and you know A, what you're really solving for is V bar. And this harkens back to fluid mechanics. V bar means the average velocity. It's not the velocity at a certain location. It's just the velocity across the entire cross-sectional area. Another thing that we have to contend with, in addition to the fact that velocity is different as a function of depth and as a function of where you are at in the channel. I mean, remember that the water is moving faster in the center of the river than it is at the banks. And maybe you've noticed that if you've gone swimming in a river before, that you can swim in the water near the banks and it's not moving too quickly, but then if you get further out into the center of the stream, the water starts moving quite a bit faster. And the reason why is that the further away you are from the surfaces that are imparting resistance to the water, then the velocity is increasing. And we have to account for that, the effect of differences in the roughness, when we try and come up with a composite end value. This is showing a channel that also has floodplains on either side. And if you think about the types of things that are likely to be found in a floodplains area, there can be vegetation there, buildings potentially, cars, all sorts of debris that's going to have a much higher roughness effect than the relatively smooth materials that are inside the normal channel area. So in the channel itself, it could be at the bottom there, clay, a soil, concrete if it's reinforced in some way. Side slopes would generally have riprap, which is like a rubbleized concrete. It might be reinforced with some vegetation to try and prevent scour and erosion. But the floodplain oftentimes will have some kind of development or a lot more vegetative growth on there because the water's not always up in the floodplain. It's only during a real wet weather event that the water's going to spill out of its normal banks and onto the floodplains. And so since there's such radically different end values, there's a lot of different approaches to calculating a weighted average. And I just wanted to show you one of the methods that's identified by the book. The Horton-Einstein method says that what you can do is you can calculate a weighted end value on the basis of wetted perimeter. Because the theory of this is that it's the wetted perimeter that imparts resistance. It's not necessarily the cross-sectional area that's imparting resistance, but it's the water's contact with the actual length of some surface that's not moving. And so you can see that you multiply the wetted perimeter of any segment by the corresponding end value for that segment, and you'd add them all up, and then you divide by the sum of the wetted perimeter. And so if you have a really long 100-meter segment, in this case, of a high end value, then you'd multiply the 100 meters by whatever the end value is for that segment, and then you'd break each of these pieces up into any place there's a different end value. You'd calculate the wetted perimeter individually and come up with a weighted average in that way. Some of the programs that you can use for open channel flow, the most popular of them is a program that's called HECRAS. Use end value weighting like this, where you're going to assign different end values to different parts of the channel. So it kind of handles it in the background, but it's still something that you need to be aware of. All right, so here's Manning's equation, and let's consider the issue of channel efficiency, because sometimes channels are natural, and in other cases you're designing them. And when you're designing a channel, just in the same way that you want your pipes to be the most efficient, you want a irrigation canal or a stream to be as efficient as possible. And by efficient, what I mean is it's able to carry a lot of flow with minimizing the cross-sectional area, because it's the cross-sectional area that costs money to excavate, costs money to purchase the land, and so on. And so looking at this equation, let's say that we want to maximize the amount of flow rate that can be accommodated by a channel. And if we leave the n constant, because that's just based on the material we're using. So if we're going to install a concrete channel, then that would give us an n value of maybe 0.013. The slope, you don't really have control over the slope often, because the slope is just governed by how steep the land is in that area. So a hydraulic designer can't say, well, let's just make the stream steeper, and then it will carry plenty of water, because if you make the stream steeper, then it's going to go underground, and that's not realistic. You can't have your river getting deeper and deeper and deeper compared to the surrounding land, especially because eventually that water is going to have to match up with whatever is accepting the flow. And so maybe it's a lake, maybe it's the ocean, so you can't have the river below the ocean when you get to the coast. So you don't have control over the n value. Well, you do, but there's only a limited number of materials that are out there available for constructing a channel. You don't have control over the slope, really. The way that you maximize the flow rate, if you look at the function, the only other variable is wetted perimeter. So wetted perimeter is in the denominator. So if you want a big Q, what do you have to do to P? You have to make P as small as possible. Now what's on the screen here is 4 different channels, and all of them are 20 square meters. So if this was all the same material, if they were all concrete, and it has the same cross-sectional area, and if we lay it out on the same slope, would you expect that the flow rate's going to be the same for each one of these? If you look at Manning's equation, would the flow rate be the same? No? Why not? I mean, it's the same cross-sectional area. The water has the same, the same area to flow through. What's going to be the difference? Yeah, why does that matter, though? Think in a physical sense. I think you see it from the equation standpoint. They have different wetted perimeters. Like the wetted perimeter of this one is 10, 22. So 22 is this wetted perimeter. This wetted perimeter is 2, 12, 14. Okay, this wetted perimeter is 4 plus another 4 gives us 8 plus 5 is 13. So you see that the wetted perimeters are different, but so what? Friction, right. So this is going to have a lot of friction. The water that's in here is not going to be able to escape the influence of these side walls that are stationary. In contrast, the water that's flowing through this channel, like in the center here, there's this whole area that's relatively far away from those side walls that aren't moving. And so the center of this channel is going to be like a good zone for getting a lot of flow through, because there's not as much resistance, because there's less wetted perimeter. So what we're going to do is just take a look at the actual flow rate for each of these different shapes, and we'll see what is the effect of the wetted perimeter on that. All right, so what I'm going to have here is a rectangular channel, and all of these we'll just use the same slope. We'll use 0.01, and these are all going to have the same n value. Let's just assume that it's a typical concrete, 0.013. And then we'll compare the different width, the different depth, the cross-sectional area, we'll determine the wetted perimeter, the hydraulic radius, and then the Q in terms of cubic meters per second that comes out of that. Okay, so this first one has a B, which is the bottom width of 2. Then this one has a bottom width of 10, bottom width of 5, and 4. So that's what we're comparing. The water depth in the first one is 10 versus 2 versus 4 and 5. Now I think, in my mind, I've done the math correctly, that these all have a cross-sectional of 20, but let's just double check and make sure that the cross-sectional area for each of these channel configurations is 20 square meters. All right, it is. But they're going to have different wetted perimeters. So the formula, since I made it easy on myself, this is rectangular geometry. So wetted perimeter is just 2 times the depth, 2 times the depth plus the width. All right, so we've got the wetted perimeter for each one of these. And now the hydraulic radius is A divided by P. So we get a different hydraulic radius in each case. And now Q. I'm going to type in Manning's equation. So Q is area to the power of 5/3 times the slope to the power of 1/2 divided by the end value divided by the wetted perimeter to the power of 2/3. Okay, now barring any typos, we'll see that the flow rate for this first section is 144 cubic meters per second, but our most efficient section, I mean, I think we can see that it's probably going to be one of these two, right? Most efficient. Let's see which. It's the one that's 5 meters wide and 4 meters tall. So this is the best of the 4 options, but what's the best that can be achieved? Like, what's truly optimal is the question. Is there some configuration that gets us even a better flow rate than that? So what if we want to limit it so that the area has to be 20, but what we can change is the combination of the depth and the width to find out the flow rate that's going to be maximized. And the question of what's the most efficient cross-section is the one that minimizes the wetted perimeter. And if it's a trapezoidal channel, then the best, most efficient geometry is one that approximates the shape of a quarter circle. And so the wetted perimeter would be as a function of the depth. It would be 2 times the square root of 3 times the depth. The bottom width you could find also as a function of the depth, the cross-sectional area, and so on. The thing that's unusual about the best trapezoidal channel is that the horizontal component of the side slope is pretty steep. It's going to be, you know, this 1 to T ratio. It's going to be steeper than a 45-degree angle. So the square root of 3 divided by 3, what's that in real numbers? I don't think in terms of square roots, not very directly. So the square root of 3, 0.577, right. So that means that for every unit of vertical, we only have 0.577 units of horizontal. So it's so steep that it would be tough to achieve that steep slope with soil, because remember, there is a shear force that's applied on the sides that is going to be greater than the cohesive force of the soil, and so the soil would kind of crumple into the channel. It could be achieved with concrete or rock or metal or wood, any sort of a material that has real strength to it. But you can't achieve generally the best trapezoidal channel, the best meaning most efficient, where you're maximizing the flow rate. You can only achieve it for engineered materials. The other shapes that are most hydraulically efficient are also known. So the example that we just looked at with Excel was rectangular. And so let's see if we optimize, if we could squeeze a little bit more flow rate out by changing the area and the wetted perimeter. So what this is saying is that the cross-sectional area of a half square is going to be 2 times y squared. The wetted perimeter is going to be 4 times y. And then b, meaning the top width, is 2 times y. So we have an area of 20. That was kind of the common thing in all of our comparisons that we did on that spreadsheet, is all of them had the same area. So if we know that the area is 20, so A equals 20 square meters, and we're doing the half square, so the area is going to be 2y squared. So in other words, 20 meters squared is 2 times y squared. So we can solve for y, and it says that the ideal depth is 3.1623 meters. Well, let's see if that's ideal. Let's go back to the spreadsheet here and test it to see if we change the depth so that it is 3.1623 meters. And we need to make sure that this gives us the area of 20. So I'm just going to real quickly do a what-if analysis. Data, what-if analysis, goal seek. And my goal is the area has to be 20. And what I'm going to do is I'm going to solve for the width that gives me the cross-sectional area of 20. Okay, so that means that the combination of, oh, that's funny. I should have just looked here for the B, right? It's 2 times y. I didn't have to do a what-if analysis for that. But anyways, that is higher, right? Previously, the best one that we saw was 205 cubic meters per second. What this says is that if you go with the half square, then you can squeak out 208.8 cubic meters per second of flow capacity for the same cross-sectional area. So the take-home lesson is that when you're designing a channel, you don't want to design one like this. That would be really tough for the contractor. Think about the excavation required. People would be falling into that pit, and it would be collapsing as they're trying to excavate it. It would be really a nightmare. Now this one they'd love because it's not too deep and it's easy to build, but it's not as hydraulically efficient. And not only that, not only is it not as hydraulically efficient, a 10-meter wide right-of-way that's meandering through potentially agricultural areas or neighborhoods, it's going to be really expensive from a real estate perspective. Out west, it's far more common for them to have irrigation canals. But throughout Colorado, Arizona, Utah, a lot of the Mountain West, there are these canals that go through people's neighborhoods, and they're delivering water from the mountains to cotton fields, corn fields, just all sorts of productive agricultural regions. But you want to have it be as narrow as possible because it's really expensive to buy up all of that land. All right, so let's have you get a little bit of practice with this, and let's go with the triangular cross-section. So what's going to be the flow depth? What we're trying to do is accommodate 2.5 cubic meters per second through a concrete channel that's set out on a 1% slope. So what should be the flow depth in that situation? So for the triangle, instead of A, you put in y squared. Instead of P, put in 2.83 times y. And then you solve for y. All right, so the best triangle, again, is one where the area is y squared, wetted perimeter is 2.83 times y. So in Manning's equation, we just substitute in both of these formulas in for A and P. Everything else is fixed, so the end value is known, the slope is known, Q is known, and when you use the solver, you'll find that the depth in this case would be 0.851 meters. So that is how we maximize hydraulic efficiency, at least for open channel. All right, well, let's take a look at the announcements before we finish up. Remember that the homework assignment is due on Tuesday, and we're having a quiz. And man, I sure have emphasized how important it is to be able to solve trapezoidal geometry and Manning's equation. So I hope I haven't bored you with those constant exhortations, but it'll all come to a head on Tuesday when we start our class with a quiz. All right. Have a good day. I'll see you then.